Okay, I take over. I'm Martin Buchholz from Watergy in Berlin, and I show a bit about a building demonstrator we have built in Berlin-Adlershof. And we did this together with Technische Universität Berlin, TU Berlin. Marco, can you give me the control?
You should have control now.
Doesn't work.
Yeah.
Yeah, okay. So here you see some pictures. So it's a twin office container we have built just as an office, also used. And you see on the upper picture a facade greenhouse we added. So also in this project we have a greenhouse, but this is not a must. And here a view inside. We have a quite big area. Maybe a fourth of the surface is our experimental area for the system we are using. And we are showing now the applications for the heat supply, but also is used for cooling in the summer. And then always in combination with humidity control, which is an added service for the building, which normally you only have in very expensive systems. And the third thing we look on is we try to have a water recovery from the greenhouse air, and we use this water for evaporative cooling. So our source of cool is evaporative cooling in combination with heat pumps, as I have to say, for some cases. And then, of course, we're using the desiccant for the drying part of cooling. Here you see the two schemes. On the upper one, you see the heating function, and on the lower one, the cooling function. It's very basic explanation. So in the middle, you see the heat pump we are using. So you see my pointer. So we have the absorbers. You saw the absorber from Switzerland. Here we have a similar element. And the most simple system is just that we have circulating air from the building through the absorber. And what is happening is that we reduce the humidity and convert latent heat into sensible heat. That can be interesting if you have some humidity sources in the building. That can be high attendance of people, can be activities in the kitchen, cooking and so on. Or in special uses, like in a swimming pool or so, of course, you have other humidity sources. And you convert it instead of removing the air to the outside. And this normally is related to ventilation heat losses. And you are, in principle, you can reduce it to zero ventilation heat losses. Of course, then you have also to remove CO2 in the end. And then you also have to aerate again. And then you also need heating. So we add heat from the heat pump to the solution, and we are heating the air with the solution. So this is also our radiator in the building. So it's also the idea of having a cost-effective system where everything is running through one system. And the difference to normal heaters is that we have a direct contact between the liquid desiccant, the thermochemical fluid, as we call it, and the air. This means that also the fluid is a kind of wet filter, removing particles, VOCs, let's say, and of course the humidity from the air. It's also cleaning the air, and by this gives a better quality of air, and also again a reduction of heat losses in the aeration. Then we have a different system where we also add to the absorber the incoming air, the fresh air, and then having a partially open system. Okay, and the second thing we look at is how can we use, besides the internal humidity sources, extra humidity we're producing, and that's similar to our last question from the audience. So here we can, when we have a sunny day, we can produce latent heat in form of the water vapor in the greenhouse. And with the second absorber, we take up the humidity and convert it within the building, I have to say, to sensible heat. And either this is feeding a storage directly, this heat, or it is using the heat pump as well. And we give the, let's say on a day with low radiation, could be 20 degrees or so, and we give it to the heat pump. We can grade it up to 30, 40, 50 degrees, depending on the application. And by this, having a very effective heat pump process in this period when we have some sunlight, and we use it for filling up the storage. And by this, yes, and to have a very efficient heat pump process in that way. And that's the idea of the heating function. In the cooling function during summer, it's a bit different. So we have the second absorber, we use it as an evaporator. So we have not the desiccant fluid here, but normal water. And we use the exhaust air to be humidified and to cool the water. And the cool water is cooling the desiccant cycle. And by this, we can have a kind of natural cooling process. This is a very simplified scheme. For example, we can also use the cool from the air with the heat recovery unit to cool down the incoming air, which is here. And we can also combine it again with the heat pump for more stronger cases on hot summer days. Yes, maybe this slide is only to show here again the two absorber columns and the building. The idea of having humid air as a heat transport facility. So we in these three units you see on the left, we are evaporating water. We already seen the example of the greenhouse where the plants are evaporating the water. You can also imagine like a PV photovoltaic collectors, which is humidified on the backside, by this providing latent heat from such an installation and the possibility to take the humidity up in the absorber and converting latent heat to sensible heat. And this means the water here on the backside is actively cooling the surface. In summer, it can increase also the electric efficiency of the collector, but in winter, by cooling the surface, we also reduce the heat losses. In theory, we have not done the research on the PV, but on the greenhouse, we can also show that by this we are increasing the collector efficiency by cooling it down and converting to latent heat. The latent heat is not occurring losses, so this is also kind of energy storage from here to the right. And then finally, it's not a must, but of course you have also periods in the winter without sun. Then you go to more conventional system using ground heat, and this can be done directly, conventional, but also there are some possibilities to use the same principle and to have also an air cycle through the ground and having evaporation by increasing the heat uptake from the ground to the system. This can be, for example, interesting if you also use the ground heat for cooling in summer and also have some evaporative cooling there. This is maybe a bit more special, but the basic principle maybe is more the solar uptake of. So you see, normally absorption systems are more known for cooling applications and for the drying part of the cooling. And here you can see that we have explored some different means of heating systems, which are quite innovative. I now turn over to also a video, so it's not a professional one. It's just to show you the system on place, and then I finalize with these few slides on the results. Marco, you're already active, I think. Demonstrator in Berlin, Adlershof. We try here to demonstrate and to do experiments on thermochemical technology used in buildings. I think this is the main function for heat networks, so it's also important to show that we can provide the services of heating and cooling in buildings with the help of liquid desiccants with the thermochemical fluids. We are here in the building and we have a view into the facade greenhouse from the inside. We use in winter, today is a winter day, outside is around -2 degrees. But the sun is shining, there is a nice temperature in the greenhouse and it's very humid. We have a lot of plants there. And what we are doing is we are using the latent heat of the humid air to get heat, solar heat, and to provide it to the building. And that's what we are doing here inside the absorber. This is the place where our thermochemical fluid is in action. So it's running through these cylinders and it's getting in contact with the greenhouse air. And by this, the hygroscopic property of the desiccant, of this thermochemical fluid, allows us to capture the humidity and by this to change humid air, latent heat, into sensible heat. We can see how the liquid desiccant is provided to the absorber surface distribution element. Here you see one of these columns in action. The sensible heat is heating the fluid and is getting in contact with the heat exchanger, and then from there we can bring the heat into a thermal storage. So through a few hours of solar radiation in winter days, we can provide heat for the whole day in the building through the heat storage. In our system we have two columns with absorber functions. And the first I've just explained is for capturing the heat from the greenhouse. Now the second is our heater in the building. So we can provide heat either by circulating air, so the air from the building goes through the column, is heated by heat from the storage. But also we can control the humidity to a very precise level. The liquid desiccant, our solution, it can dehumidify the air from the building when a lot of people are inside, for example. But when it's very dry here, it's going the other way. It's humidifying the air. You can do this very easily without steam, without spraying water. It's also very hygienic because the salt solution is kind of biological inactive compared to water.
Here we are in front of the monitoring and control unit of the machine. We can here control the different actuators, pumps, ventilators and ventil valves, as well as check the temperature levels, humidity levels and flow levels. On the screen on the left hand side we can see more than 50 sensors telling us about the machine states, and on the right hand side more than 30 actuators including valves, pumps and ventilators that are able to drive the heat where it's supposed to be.
Here we are at the regeneration unit of the system. On the very behind you see the residual heat device. So we have some hot air coming from a cooling process, from a machine cooling. Just capture this air which is normally unused and bring it through our desorber. That means we have some heat in the air and it's getting again in contact with our thermochemical fluid. The water in the solution is evaporated and going out through this tube. That means that we are reconcentrating the solution, and this is our energy carrier, and we collect it here in the tank. from here it's pumped back to the building, and vice versa, we are getting the diluted solution from the building and use it here in the regeneration unit. Okay, I think we go now back to this to the presentation, and I show just one day a few results to show the idea. On the left, you see a graph with the temperature. So you see very nicely how the temperature in the greenhouse, the green curve, is going up. The blue one is the ambient temperature, and the red one is the temperature in the building. And the system started, I think, at 9 o'clock or so. And you already see the source of heat in the greenhouse by the temperature, but on the right side you see this is temperature, the sensibly plus latent heat, so the enthalpy in the system. So you see that there is even more energy compared to the state of air in the building, and that's what we are using. And next slide, I have again lost my control.
You should have control.
Yeah. Or can you just switch it?
Okay.
The next slide.
Yeah.
The next slide here, very good. We see now the system in the absorber. So on the top we have again the temperature. So the green top is the incoming air from the greenhouse, and the outgoing is the middle curve is just what the difference is, what we bring back to the greenhouse. So the same for the water content in the middle. So this represents the latent heat part, which is just also quite a difference, and then resulting in an energy flow of around 2 kilowatt in maximum in this example. Okay, I think this is more or less my presentation. I don't know if I have time for questions, or if you put it to the end.
I will continue, Martin. Thank you, Martin,
Okay.
for giving us insight in the Berlin demonstrator. I have only 3 slides about the transfer of that to Hasselt and to the building stock of Hasselt, and then we have time for question discussion about the use of some technology in buildings. Yeah, I have control. That's working fine. Thank you. Yeah, what we did was basically using the scheme and the technology that has been developed for Berlin and transfer that to the building stock of Hasselt. So we had the question, so what if the technology is applied to selected areas of a city? And we had a close collaboration with the city of Hasselt. They gave us data of 15,000 buildings, demand data, and building shapes, building geometry. And from these data, we extracted information about typical demand of such average European city, and compared what if we use first the thermochemical system, second conventional gas boilers, third standalone heat pumps, and fourth the conventional district heating system with hot water in the pipes. We have projected a network that covers 155 gigawatt hours per year of the heat demand. That's approximately 42% of the coverage. That was necessary because it's not, you wouldn't apply a network to all the buildings that belong to Hasselt, but more or less the center as you see it here on the right. To carry out that case study, we divided the buildings of the city in 3 clusters, and were clusters with low heat demand, with medium heat demand, and with high heat demand. And so it was easier to develop the system in a way for one building per cluster, and then scale that up for the whole city to represent that and to calculate the pipe diameters and related costs for all the systems. Maybe one important thing is that both the thermochemical system and the district heating system were based on excess heat from industry, run by excess heat from industry by a plant. The case studies included a plant that is 50 kilometers outside the Albert Channel. It's difficult to see here, but there's a channel in north of Hasselt, and that is connected to a plant of Arubis in Olen, and there is a lot of excess heat available, and ship transport of thermochemical fluid to Hasselt was included. The result of that case study was that we have we looked at the CO2 emissions first. There you see that gas boilers, of course, have the highest CO2 emissions. Standalone heat pumps have lower emissions to the COP of that devices. And lowest emissions are the both network system, thermochemical networks and conventional district heating networks using the excess heat from the plant in Olen. If you look at primary energy, you see approximately the same distribution, high primary energy for boilers and lower energy if you go to the excessive utilization. The bit higher CO2 emissions and primary energy use of the thermochemical system is caused by the pumping and the combination with heat pumps to cover peaks in winter, which is difficult by the thermochemical system. If you have a look at the analyzed project costs, we see that the gas boilers and the conventional district heating system is the cheapest solution for Hasselt. That depends, of course, on the excess heat that is available and on the cheap gas, the technology for the gas boilers. And heat pumps are the most expensive solution, and thermochemical systems are in between. With that result, we also went through the countries in Europe and ask ourselves what happens if we go to different locations, different countries, different climate, different market conditions. And I want to draw your attention on to one case, that is Sweden. In Sweden, we have a quite high gas price and relatively low emissions for the electricity. So the electricity power mix has quite low CO2 emissions. And in that situation, the thermochemical system works quite well. It's even cheaper than the gas, the conventional boiler of gas, and that is a thermochemical system. Yeah, that is a transfer to Hasselt case and the heating and cooling solutions for buildings. And now we have time for questions. Let's say, yeah, it's 5 minutes for questions. Are there any questions for heating and cooling in buildings?
Hi. Just one question regarding temperature levels. Are there any constraints using H-DisNet technology for space heating and domestic hot water preparation?
Maybe we have two dimensions. One is the regeneration process, and this is related to the outside humidity from the ambient air, and which has to take up the water from the fluid. And there, in the wind time, we can work with very low temperatures, like 20 degree to 30 degree, because the outside air is very dry if it's cold. Whilst in the building, we are somehow related to heat pump technology. We think about heating temperatures of 30 degree, 35 degree, 40 degree in this range. So low temperature heat systems are required, and already a quite good building insulation standard. So it's not so good to be used in retrofitting of or let's say semi renovated buildings or low quality energy efficiency buildings.
Okay,
Yeah.
thank you.
Okay, maybe to add to that, especially the low energy, near zero energy buildings are quite interesting candidate, and I mean that's the intention of the EU to develop and to implement these buildings in the building stock. And exactly for these buildings, a quite interesting solution because it's a low temperature system, low exergy system. It has further capabilities of cooling and also including the humidity control.
Mm-hmm.
But not only passive house standard. So if you have very low in energy consumption, of course, the effect you have with these systems is from the financial point is also not so interesting anymore. But maybe buildings with 40, 50 kilowatt hours a year per square meter, this could also fit quite well.
Mm-hmm. Okay, and for the domestic hot water production, the system needs to be coupled with another system, or are there any way to produce domestic hot water?
Yes. So of course, this is always a problem with the Legionella. You want to have 60 degrees all the time, but there are also now some innovative solutions working on 40 degree and having a heating of water very close to the user places, and so so it goes in the same direction to get to temperatures of 40 degree, or only to use the heat pump, let's say every 2 weeks to heat up the whole area to 60%, and then work things like that.